This is ideal continuation of my GHM 2017 talk, in which I showed the possible evolution in complexity from an interpreter to a JIT compiler using Jitter as an example. Here, I will show you the difficult part. I will show you something about the difficulty of having a JIT generator, which is in fact Jitter. And I will try to give you an idea of the internal complexity that it requires. And starting from this, we will discuss about the problems of complexity in general and whether there is hope for the future or not. So, this slide is mostly for people who will watch a recorded version of the video and want to reproduce my demo. So there are archives to download, and those are also available thanks to Jose at the meeting homepage. So Jitter has a history. I wrote it in order to speed up a language implementation, no epsilon. I was dissatisfied after trying the common tricks consisting in writing fast interpreters with threaded code. And so I started reading research papers to accelerate them, adding my own ideas until the project exploded out of control and it became something reusable and independent. Soon enough after I showed him, Jose decided to adopt the project as the core of POKE, and I thank him for his trust. And then there was the famous presentation of GHM 2017, which is linked in the bibliography at the end of the slides, and people who watch a recorded version of this may be interested in following. Now, click. Okay, yes, Jitter is used by POKE, and it was recently accepted as a part of the project GNU in its own right. Now, I will start with a long demo about the structured programming language. So structured is, in fact, one of the examples distributed along with Jitter. It is not an interesting software by its own. It is boring and didactic, which is intended to be. It is an implementation of a programming language in the style of Pascal, imperative with variables, only integers, conditional loops, and recursive functions, and that's it. It is very boring, but very easy, very clean, and that is its real purpose. It is, in fact, so clean that I could afford the luxury of implementing it twice, one with a stack-based virtual machine and one with a register-based virtual machine. It also comes with a nice example of how to use Jitter from an external project. So the build system is clean and uses Autoconf and Automake. I will show you a taste of Jitter starting from it, and I hope to convince you that this is relevant by making it clear how easy it is to make something reasonably fast. So I will now start screen sharing, and you should see at this point my terminal. Don't care about this. Okay. And so here I am in the build directory of structured. And if I look at the bin subdirectory, I find that there is one executable. This is structured. I can call it with -help to get the command line option documentation and so on. This is all very boring. Now, in order to do something interesting, let me run using this, which behaves as an interpreter, but trust me, it's a JIT. I will run an example. An example is in this directory, I think, and I will run an example which counts prime numbers below a certain limit. So this is the source code of my example, all of it. The code is just this one page. And this will tell you how many primes there are below 2 million. Okay? So in order to convince you that this implementation is fast, I have a version of the same program, the same exact program written in C. And this is the same algorithm translated line by line. I could even show them side by side if I wanted. Count primes, count primes, C, and there on the right, I will show you the other version. Okay, so we have structured on the left and C on the right. You can see that there is a while loop containing another while loop containing a conditional, and then another conditional out of the inner while. Okay, they're exactly the same structure. Very good. Now I compile this with the standard -02 option, and the count primes in C takes. I have to trust my computer, which is not necessarily the case. Here we have this ridiculously heavy weight web application, which we are using for the presentation. But if we have to trust it, it takes 1.7 something seconds in C. I will run it once more. Yeah. Now I will do the same thing with structure, and the source code was here. So when I measure the time here, I also count compiling as part of runtime. And it should be very close. Okay, a little worse than I expected, but let's run it once more. Okay, it's a little worse than I expected. I was unlucky with compilation options, I guess. Anyway, it is comparable. There are, in fact, as I promised you, two different JITs inside this executable, one running on a stack VM, one running on a register VM. The stack version will be less efficient, as you may guess. And if I remember correctly, it is not the default. Yeah, in fact, notice that the result is exactly the same, but okay, the runtime is different, and this should be 2.20 something. Yes. Okay, so I show you that this is similar to C. Okay, I could have tuned it a little better, in fact. Now, I show you this. This will give you a listing of the VM instructions I compiled the source code to. So this has been generated by my code generator. The generation of this is not part of Jitter. This is something I wrote, and I could have written quickly as a simple compiler. Now, let me open the editor and show you just a quick eagle's eye view of the compiler. So I will show you the structured code generator based on stack, because it's simpler. And as you may guess, it works by recursion. If I want to translate a program procedure, well, this works by essentially translating a sequence of statements. The program is a statement. Let's look at how statement translation works. And in order to translate a statement, I have to do a case analysis. And so according to the shape of the syntax tree, I can translate in different ways. If the program is a skip, if it's empty, I do absolutely nothing. If it's a block, it means that I have to create a variable and then compile a statement in the environment with that variable. At the end of the statement, the variable dies, so I unbind it. If it's an assignment, well, I have to, an assignment is variable color equals expression, right? So I have to first evaluate the expression, then store into the variable. So the main part of this is the compilation of the expression in the current environment. And then, well, I have to pop the result of the expression from the stack into the variable. So I will generate an instruction which is pop stack into a certain register, and this register is the register which corresponds to the variable. If I have to print an expression, well, I have to evaluate an expression. The result will be on the stack, and then I will generate the instruction, which is print stack. I can give you an even simpler example live. So I will run and print a program which is read from the standard input. Minus here means standard input. And so I will print the result of the evaluation of 2 plus 2. Control D to interrupt the input. And so there is a branch to the next label. This is suboptimal, but who cares now? Plus constant 2 and constant 2 into register 0, print register 0. What is the problem here? The problem is that this is not stack code, this is register code. Okay, I made a mistake by forgetting to add the minus stack option. There you go. We do exactly the same thing, Control D. Now, I push 2 on the stack. I duplicate the top of the stack. I run plus stack. Plus stack serves to replace the topmost 2 elements of the stack with their sum. And then I print a result. Well, this dupe is not obvious at all. Why was it introduced? It was introduced because this comes from an optimization rewriting. Is the kind of easy optimization I get essentially for free by specifying in the VM description that some sequence of instruction is equivalent to a faster sequence. So push 2 is equivalent to push 2 only once, duplicate. I will rerun the same program, print 2 plus 2, by disabling optimization rewriting, just to show you. This does exactly what we think. It pushes 2 once more. It executes the sum of the 2 topmost elements. So on the top of the stack, after the execution of this, there is a 4. And print consumes the 4 and shows it into the output. Very easy. If I wanted to, for example, make a variable, I could say that var x is initialized as 25. Then I will set x to x plus 1, and I will print the new x. This will print 26, and the program should be pretty readable. So it pushes 25 on the stack, popped into the register R0. From here we understand that the VM register R0 contains the variable x. I push R0 back to the stack. I push 1. I replace those 2 elements with their sum. I pop back into R0 in order to execute this assignment. Then I push again in order to have this argument, and then I print. You see that this code is very redundant. There are many simplifications that will be possible. And a lot of these simplifications are executed by optimization rewritings. I will show you the same with optimization now, just to show you. Yeah, and you see that the program is much nicer and much smaller. Of course, it will be even nicer and even smaller if instead of a stack I use registers. And here I have just one constant loading into a register, plus register and constant into the same register, print register. This is super nice. Okay, so I hope I gave you by this very quick overview, I hope I conveyed the idea that this compiler is very, very simple, and you could write it in one afternoon if you know the API a little. Now, the point is, what is that Jitter gives me to make this job easier? Well, all these structured VM procedures that I call here are in fact generated by my code generator. So Jitter takes a VM specification and generates some C code that then I can link into my application. And this C code contains, for example, code to generate labels or to append instructions. This is, of course, a procedure which has been defined by my generated code. It has not been written by hand. So whenever I have to append an instruction, such as this branching instruction, and then an instruction parameter, such as a label, and so on, I can just call a generated API. Now, I would like to show you the VM definition, which is here. This is the Jittery VM for the structured language, which is a little more big than one could imagine, because there are in fact two VMs inside. There is the there is the stack logic, and there is the register logic. In fact, I'm only using one at a time, but I chose to have just one VM. That's arbitrary. So there is a stack that I can use either for parameter passing when I call procedures, or for evaluation as well, in the case of stack evaluation. In the register code generator, I use the stack only for parameter passing and for return addresses, not for this expression evaluation. Now, let's look at instructions. This is the interesting part. And even if I didn't show you the register-based compiler, you understood, for example, this plus instruction. This is a very good example. It has two inputs and one output. The first input can be a register, and then it can be either a second register or a constant. Here there is a constant. The output is always a register. Okay, so let's see how this is defined. This is a plus with 3 arguments. And if I look for instruction plus, I should find it. It has 3 arguments. The first 2 are input. You can see this question mark. Question mark, this is an input parameter. Bang means output parameter. So the first 2 can be either registers or a literal. And the code is this. Now, this may not be entirely obvious because I'm using some macros, but the code between code and end is in fact C. So this is C using a few predefined macros that come for free. And this macro allow me to refer the arguments. So here, the third argument, we count from 0. So this thing becomes the value of the first argument plus the value of the second argument. Okay? And so I had this. Now, I could even disassemble instead of printing. Let's do both. I will print and disassemble. Exactly the same program, and just cutting and pasting here. And here we have the same code, and here we have its disassembly. Let's look at plus. So this VM instruction becomes this native instruction, incqr13. So we notice that the VM register R0 has become R13. R13 here is x86-64 register. We're speaking about registers of the hardware machine, which implement registers of the VM. Okay? So this is a pretty good implementation of plus. I would say that it cannot be made better than this. Notice also that this only works with 1 as the constant to add. This instruction has been specialized, and you will see what I mean in a little while. I will show you a different example. I will add 2 instead of 1. Then I will print x. Exactly the same program as before, but instead of adding 1, I added 2. And you will see that the compilation into VM code is exactly what I expected. And the compilation into native code, now it no longer uses incq, but uses addq with 2 as an immediate argument. Again, it is impressively good code. Of course, it will not always be like this. It will not always be this good, but sometimes it is. Before ending the demo, I would like to show you one last example. I want to show you a loop. So let S be 0 and let I be a counter. While I is smaller than 10, I'm sorry for this notification that gives me And for the presentation, I will do it. I will declare these two variables. Then while I is smaller than 10, I do s becomes s plus I, and I becomes I plus 1. At the end, I will print s. So this should print the sum of the numbers between 0 and 9. Right? 45, it works. Now, you can see that this language, of course, supports jumps and labels. It's very similar to an assembler. You can move constants into registers. You have arithmetic, as you saw. You have jumps, which can be unconditional like this, or conditional like this. BL means branch on less. If R1 is smaller than 10, then we branch into L4. And so this is the implementation of the loop. See? There is one reverse conditional at the very beginning, which is to skip the entire loop if the condition is false at the beginning. So if R1, which is the variable, is bigger or equal than 10, then we jump to L8 and we skip the entire loop and directly arrive at the print. Now, if we look at the disassembly for these instructions, you see that, for example, well, plus is very nice. Look at the BL, branch on less. This is not so nice. There is this instruction loading a constant into a temporary register, R12, then a comparison between this temporary register and a variable, and then a branch on less. Okay, so there is this, which is a little unfortunate. You will see in a little while why this is needed. But I hope I convinced you that this is, in fact, some reasonably good code, and I obtained it with little effort. By the way, the printing and even the disassembling of the program all come from free. Jitter gives you all of this. Now, how can I actually use this? I will show you from the structured source distribution, the configuration script, for systems, I think. Configure.ac. So this is the configure.ac that you need in order to compile Jitter. There are comments, AC init, and the obvious things. Now, the interesting part is, if you want to use Jitter, you use this Autoconf Macro, and that's it. Then you include the entire Jitter source distribution as a subdirectory. Then here I use Flex and Bison, but this has nothing particular to do with Jitter. And then that's it. This is a standard configure.ac. If I look at my makefile.am, you will see that I compile my generated code with Jitter C flags. So, among the compilation options for generating bin structured, I have to include Jitter C flags. This variable you get defined for free by including by executing this Autoconf Macro. Okay, so the task for you is really simple. You have to compile with some options. And how do you generate the actual generated code? So some of this code is machine generated, and it is this. The scanner and parser are also generated, but that is not with Jitter, that is Flex and Bison as usual. So these three files, a header file, then a VM1 file, and a VM2 file, are output by Jitter. And this is the makefile rule to generate it. And that's it. In practice, all three are generated by just one command line. And since make does not allow you to have multiple files produced by the same rule, I have to do this little hack. But essentially, I call the jitter executable with the jitter file as an argument, and files get generated. This is how it works. I can tell him which directory I want the generated files in, and that's it. And yes, in order to generate the other generated files, I need, yes, Bison and Flex, and that's it. Of course, I can have a manual, but this is standard. So, super simple. I hope I attracted your attention with this. Now, I'm going back to the slides. Yes, and I show you this on my x86-64 file. No, let me go back just for 1 minute to the terminal, because I wanted to show you that, in fact, this works on different architectures as well. And all the tabs you can see here are different configurations in which I test jitter. And I have a lot of cross compilers. Here, for example, I have MIPS. Why not? Let's test it on MIPS. And I have my structured example, which is a MIPS executable. Okay, so this is JIT for the MIPS architecture that I have to run with an emulator, because I don't have a MIPS machine running here. So if I try to execute this, it will say, okay. I was surprised by the kernel, which invoked QEMU automatically. You remember the one of the presentations for the first day, that is the Beam FMT extension. So anyway, if I didn't have that, I could use my emulator script, which is just a wrapper around QEMU. And so this is just the structured program running on MIPS. And I will disassemble. We cross disassemble, because now I need the MIPS disassembler. I run from the standard input, print 2 plus 2 plus 3. And here you can see that this is indeed MIPS code. Okay? And this is also good MIPS code. It did a good job, for example, here adding, what is that? Adding 2 plus 2. Notice that I compiled, bring 2 plus 2 plus 2. Structured is not an optimizing compiler. There is only the rewrite system. But just by converting this VM instruction plus 2 and 2 into R0 into native code, we had this. So load the literal 4 plus the register number 0, which on MIPS is hardwired to the constant 0, into the register number 21, which stores the variable. So the register number 21 corresponds to the VM register R0. I hope these two levels don't confuse you too much. Of course, you have to map VM register somewhere. It can be a hardware register, or it can be memory if you don't have enough space. But you need to keep a mapping between the two. In fact, I can even show you the mapping. Print locations. So this is useful for debugging. And once more, I will show you the same program again on MIPS. 2 plus 2 plus 2. Okay, same code, but notice that now I can see that the VM register R0 is mapped to the MIPS register $22, which is exactly what we expected. That's it. I will show you on MIPS or on any other architecture, it doesn't count. I will show you an infinite loop. Show you a branch. Of course, it doesn't terminate because it's an infinite loop, so I have to interrupt it. Notice how the jump has been compiled into MIPS. There is one jump instruction and one delay slot, which on MIPS you have to have. So, perfect. This is optimal. I can show you the same code on an infinite architecture. Mohammed was speaking about PowerPC before. Let's take PowerPC. I like it as well. PowerPC. I have an old computer called GNU. So print 2 plus 2 plus 2. Of course. Notice again that this was compiled in an intelligent way. The constant 2 and the constant 2 always give 4 as a result. So we have directly 4 that has been loaded into R31, which is the PowerPC register, which in this case maps to the VM register R0, as we can see from this debugging output, and it works. Notice that the compiler did a very good job here. We have 5 VM registers, which are mapped to PowerPC registers. No memory is being used here. We are not always so lucky. Again, I will show you an infinite loop. And look how beautiful it is. So there is the first branch, which is not useful. And then this is the 2 infinite loop. From L1, I branch to the same level where I am. So I branch to the same instruction I'm executing. And here it is. From this address, I branch to, no, it isn't. How is it? No, this is it. This is it. From this address, I branch to exactly the same address. So yes, this is the infinite loop. One instruction, because on PowerPC, I don't have a delay slot differently from MIPS. Just a curiosity, but since I love MIPS so much, I will show you the R6 release of MIPS, which removed delay slots in some cases. So while you do nothing, this would be the same thing without the delay slot on MIPS as well. It's called the branch compact in MIPS parlance. Okay. This is pretty good. What did I do? I want to the presentation. Yes. So I show you x86-64, MIPS, and PowerPC, but trust me, I don't have time to show you everything, but a good number of architectures are in fact supported. Not all to the same degree, in fact, but a lot of them are well supported, and more will come, including some fashionable ones such as x86 32-bit, which is popular, so I have to support it, even if none of us like it. We rely on the binary format being ELF or COF, and rely on having GCC. So this is strong. The system is portable, but in order to be fast, it needs a known architecture, a known binary format, and GCC. And what happens if I don't have that? Sorry, I always make a mistake when I try to change slide. It happens that Jitter can use an interpreter instead of a JIT. We gain simplicity and portability. The behavior is exactly the same, but instead of having a JIT, we have an interpreter based on switch or based on goto star in GCC. Okay, that is the idea. If we don't even have a compiler supporting goto star, we can always have an interpreter with a switch. If you want more details about this, there is my old JHN 2017 presentation that shows the details of this. Today, I gave you a good justification why we can ignore it. This is extremely portable and compatible, behaves the same, but is slower, so we don't care about it. We design code to be run on the fast configurations. Then it will also run on less supported configurations for compatibility. This I said. And there is also a compromise between interpreter and JIT. You can read about, I will not talk about today. So let's take add again. This is the same source code I showed you on the editor. It has 3 arguments, of which 2 are input, 1 is output. And here I color-coded. In the source code, they are numbered starting from 0. So here in my block of C code, when I say jitter argn2, I speaking about the third argument. N means number, because sometimes I may want to see the argument typed as a pointer, but here I want a number. Sometimes I may also want it unsigned, and so there is a U as an alternative to N, but it is not the case here. Notice that the second argument can also be a number, not necessarily a register. So there is R and then there is N. N means that it can be an immediate argument. I think this is simplified compared to the actual implementation. I think the first can also be, yes, certainly. You remember the 4 example that got optimized. I will show you again. Yes, first argument can also be an N, you see. So the version I had on the slide is slightly simplified, but that is not terribly important. Okay. So that is a generic VM instruction definition. And of course, this will be mapped into every possible value of registers and literals. For any possible combination I pass, I have to be able to generate code. And Jitter does this ahead of time. So Jitter generates a huge block of C code. The C code generated by Jitter is huge and unreadable and also slow to compile, because it contains every possible combination. It contains every possible input register or literal. There can be literals as well on the left in the real case, and every possible register there. Yes, it can combinatorially explode. Here, I give you as an example one specialization where I have the register number 4 as both first input and output, and I have the constant 1 as the second input. It generates some C code, which is essentially like this. There is some local struct dot R4, so R4 is a field in a local struct, and this gets modified, assigned to its previous value plus 1. And you can see that this R4 comes from the third argument, this comes from the first argument, and the constant comes from the second. This can be compiled into assembly, and the compiled code looks like this. You saw it in practice, so you know that I'm not lying. Now, how does it work in the JIT sense? How can I make an entire program by gluing together pieces of code like that? Well, there is a label at the beginning of each compiled instruction and another label at the end. And in order to combine them, I just have to copy. That's apparently easy. I do an mcopy, yes. I do a memcopy from this label to the last one. Memcopy doesn't want a trailing pointer. It wants a size, but it's the same. So I have to compute the size as the difference between the two labels, and then copy to a destination, starting from the first for a number of bytes, which is equal to the size. And that's it. Notice that here I am assuming GCC. This end is the syntax extension in GNU C, which comes from GoToStar. This code, of course, is executed conditionally. If you don't have GCC, Jitter will work. This will work, but it will not be compiled in this way. It will be run as an interpreter in a different way, but it will behave the same way. So in this configuration, I can afford the luxury of writing GNU C. Now, you show in the slides example that this instruction only admits the constant 1. Okay? So what happens if I try to use a constant which is not among the constants which are listed here? So even if I do every possible combination, I will not be able to do the constants that I have not listed. Otherwise, the combinations will be infinite, or infinite in practice. I certainly cannot have 2 to the 32th 2 to the 3 seconds cases. Well, the generated code looks like this. I first have to load the constant into a temporary register and then use the temporary register as an operand. So here I have to load 3, which is an unforeseen, one could say, argument into a temporary register, which is here R12, and then do the usual add. Okay. So this is a less nice case, but by listing here the literals which I assume will be common, I can make the common case fast, and I can still support the less common cases. This is why in the loop counting up to 10 that I show you as an example, there was some inefficiency because I needed to load 10 as a constant. 10 was not specialized for. So these arguments which are not specialized for, I called residual, and the specialization of an instruction having residual has these big R arguments there. So this costs a little at runtime because we have to insert code, and this code has been generated by Jitter. Well, it has been written by me. I mean, I, as an author of Jitter, has had to generate assembly code in order to load every possible constant. And so there is some assembler code specific to the architecture which is able to materialize into a register or into memory a given argument. This works for tree in a way, but it can work in a different way for different constants. For example, on x86 64, there is a fast way to load the constant 0, which is by XORing a register with itself. That is the standard trick every compiler uses. So if I want to load a temporary register with 0, I can do XOR L of itself. Notice the XOR L also clears the high part of the 64-bit register. I will not show you the details of assembly. I'm assuming you understand here. But the idea is that I just give you a pattern that I can follow in order to load some constants. Okay? So, for example, if MIPS has a faster way of loading 16-bit constants, then I can have a different case. And when my constant fits in 16 bits, I can use the shorter and faster sequence. And when the constant doesn't fit, I will use a longer and slower sequence. This is not optimal, but it is the best I can do without having every possible combination. Without having every possible combination. So, also notice that I need to reserve a hardware register just to hold this constant that I will load. And yes, as I told you, it is architecture specific, a little painful to implement for me, but for me, this is the beauty of the thing. Jitter gives you this for free. You don't have to write this logic for every VM. When I write VM code, when I write a VM specification, I can write something very, very nice like this, and forget that some constants will be slower than others. They will work exactly like the rest, exactly like 1, even if they will be slower. Okay, so how do we jump from a VM instruction to another? One way would be by materialization, which is by this trick. I could load the target label into a temporary register and then do a jump via register. That works. And in fact, I used to do it. It worked so well that Jitter used to work like that. Of course, it is slow because I have to first materialize a big constant. Labels are usually not small numbers. And then I have to do a jump via register instead of an immediate jump. So you have to pay some performance for that and certainly some code size. So it is better to avoid it. And if I want to avoid it, one way is to generate an instruction like this. The problem is that I don't know the label where to jump to, so I have to patch the code. I first have to compile this. I have to do my mcopy in order to paste a copy of this at the right place of the executable memory, but then I have to overwrite this destination address with the actual destination address that I only know at JIT compilation time. So this is complicated. I will not show you the details of how it works, but I will show you the main problems we have to face. First, the user needs to be able to use this without seeing assembly. The user should write C with macros, and that's it. And the VM itself should be portable. So the user needs a nice way. And of course, I need to know what is the address to patch. The difficulty here is to find the .l written in red here inside the blob of binary code. I don't know where the target address begins. In order to present to the user in a friendly way, that's pretty easy. I just have to provide macros, and the macros can contain just one argument, such as the destination label for unconditional jumps. For conditional jumps, it is a little more complicated. For example, I can say, if this expression evaluates to a non-zero value, then branch to this label. I can have even much more complicated instructions, such as execute a sum, and in case of integer overflow, branch the label instead of assigning. This actually exists in Jitter, and it is complicated. It is certainly something you do not want to implement yourself for every architecture or even for every VM, because it is painful and complicated. So in order to know where to patch, we need patch-ins, but before speaking quickly about patch-ins, I will show you how the thing looks in the actual code. So here is my source code, and I will show you branch on less, BL. So I have three arguments. The first can be a register or a literal. The second can also be a register or a literal. I specialize on 0 because 0 is common. Very often I want to compare against 0. And the third argument is a label. And the code is simply this stupid macro. I branch if the first argument is less than the second, in which case I branch to the third argument. I call these fast labels. They are fast because they never occur as values, they're never materialized. They just occur as address being patched into a branching instruction. And you can see that I have an entire zoo of these branches. I have another case for not equal, for not greater, for greater. I have every possible combination, of course, yeah, not less, and so on. I would like to show you using a different VM. I don't have overflow control on structure, but I have it on a different example, so I will show you a different example that also comes with Jitter, which is called uninspired, because it's a very boring VM. This very boring VM has a branch as an add with overflow support instruction. It has 4 arguments: one input register or literal, another register or literal input, a register output, and a label. So this output is written in 2 only if the sum does not overflow. If the sum overflow, I write nothing, and instead I branch to this label. And this is all implemented with a macro, 4 arguments. Okay, I want to show you how it works. So this is mix32R6, which I suppose is not a very popular argument, a very popular architecture. I don't think it is widely known. Okay, so I will show you on x86-64. We run the uninspired example, and here I am just directly writing VM instructions. There's no high-level language here to be compiled. This is just a program that runs the VM program encoded as text. You can see that the front end of this is an assembler, not a compiler. And this is also generated by Jitter. You get this for free if you want it. So I can show you of constant 1 into register 0. This is the assembler of the VM uninspired. And then I will print fixnum, I hope I remember it correctly, R0. Execute. Yes, it printed one, which works. And here is the disassembly. I loaded the constant 1 into the register, into the VM register R0. And notice that the VM register R0 is mapped to the x86-64 register RBP. Then I do the print. This is a call to a library routine, and then I exit. Okay, let's do an add. I will move 1 into the register. I will add R0 plus R0 into R0, x2, and I will print R0. I'm only using one register. Why not? Yeah. So the load is exactly like before. The add does an add of RBP into RBP. You know, the x86-64 is an ugly two-operand architecture. So this means RBP plus RBP goes into RBP, and then it prints. Perfect. Lovely. Now, let's see the version with overflow, because now I showed you the 3 arguments add without the label. Now, I will give you a label to begin with. I call L the beginning of the program. No, a bad example. I'm restarting. I will load 1 to R0. I call L this program point. And I add with overflow R0 into R0. So I double it. And in case of overflow, I branch back to L. So I make an infinite loop. Then if I don't overflow, I will print R0. So this should print it should print 2 without overflowing. And it works. And look how beautiful this code is. I move, yeah, my egg is laughing there. I have reasons to be proud here. I move RBP, which contains the register R0, into a temporary. Then I add another copy of it into the same temporary. And here I use the x86-64 instruction JO, jump on overflow. So here I use hardware support for overflow. Okay? And in case we overflow, I branch back to this address, which is here. So I branch back to L. It's exactly what I wanted. Right? So it worked. If I didn't overflow, then I copy the temporary into RBP, which is the R0 of the virtual machine. And then I print. Lovely. Now, let's have something that overflows. This is difficult because I need a 64-bit number that overflows. This is an excellent occasion to show you the multiplication instead of sum. So I will load something like make 4 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. This fits into 64 bits, but in square does not. First test. So this number should be printable with no problem. Sorry, it is called fixnum. It should work, and it does. Notice that I needed to materialize the literal. Of course, I did not specify for this ridiculous constant that is almost never used. But the code is correct. Now, before printing it, I will square R0. And here I will say mul O. Also, I have a mul O, which works exactly as you may imagine. Times bus friend, branch fast overflow. So I will multiply R0 and R0 into R0. Purely by conventions, my destinations are on the right, I think. No, not even sure. Who cares? It's always the same register. And in case of overflow, I go back to the same instruction. So in this case, this should loop forever. It should loop forever. And it loops. Notice once more how simple and compact the code is. I don't think it is possible to do it any better on this architecture. I want to show you another quick example. I will load any constant, for example, this ridiculously big one. Then I will do a subtraction with overflow checking. And I will subtract R0 and R0 into R0, so that will be 0, because whatever there is, I will subtract it to itself into itself. And in case of overflow, I will go to, oh, I forgot the label. Oh, yes, I will go there, even if it's later. Okay, I want you, in this case, I'm not terribly interested by the execution, but I want to show you the generated code. So, question for the audience. Tell me, what is the optimal way to compile the subo instruction in this case? Anybody knows? I'm subtracting a register into itself. It doesn't matter what the register contains. I subtract the register minus itself and I write it into itself. So of course the result will be 0. So this is exactly the same as loading the constant 0 to the register, and it can never overflow. In fact, this is exactly what happens. So the register is cleared. Okay? And so this happens because I specialize for every possible combination of registers, and when I have this triplet of registers, the optimal way of compiling it is this, and GCC knows, and I try to exploit it. So this is not just C code with some assembly snippets inside. If I did that, I would lose the possibility of doing this optimization. This is really painful to implement. I will not show you how it works. It is too complicated. Even I forgot the details. But this kind of thing is difficult, is error prone, and is important in interpreters and compilers and interactive systems. Imagine Lisp or imagine Poke, imagine something where users write code and you have to type check every instruction you execute, and you want to make sure you don't overflow. This thing is performance critical, and you don't want to do useless checks, and so you can avoid them. Good. So what is a path chain? A path chain is a technique to implement these complicated macros, and I will not show you how it works, except for the general idea. The general idea is that you expand it to some assembly code. This is some inline assembly in GNU C. But at the beginning and at the end of the assembly code, you add something to a different section. So I temporarily switch to a subsection that in this example is named 42. And in this subsection, I emit a datum, not an instruction, which is a pointer to the label I am about to fill, and some more data that I will need. Then I exit the subsection and I keep generating code. I generate empty code because this will be filled later. So this is my trick to generate empty space that I will be able to fill later. And I know what to fill because somewhere else I kept track of the pointer of the instruction to fill. Of course, this code will be copied and relocated because there is the replication part. But I know the offset between the hole to patch and the beginning of the instruction. So with pointer arithmetic, I'm able to find the hole to fill. And it really works like that. Also, this requires some machine-specific logic, which is, again, a little painful to implement. I will not show you the details, but it works. Now, what happens if I try to refer a global variable from a instruction? Well, the problem is that on modern architectures, instructions are loaded PC relative. I load the address, which is at some distance from the current instruction I'm executing. This breaks horribly if I try to relocate the code, if I try to move the code. I can give you maybe an example. No, not so easily. Okay. I will take again my Emacs and I will show you. Say that I have a variable x global. Let's invent in GNU style, which is that. I will return the current content of x as a result from f. So I want to convince you that the load instruction that takes the value of x from memory is PC relative in common code. We go to directly compile the code, it should be readable. I compile my code to assembly, optimizing, and here it is, q.s. I will show you on the right. And the instruction which accesses x is rip relative. And on x86-64, rip is the 64-bit instruction point. Okay, it's not a general purpose register. This is just a notation to say access k bytes from the current instruction. And so if I try to copy this block of code elsewhere in memory, it will no longer work because the distance between the code and x will be different, will have changed. And so that is a horrible way to have bugs and crashes, particularly if you write into variables. So absolutely, we should not have global variables like this in VM instruction code. In code like this, it is forbidden to directly use global variables. What is the solution? Because global variables are useful. The solution is defining a macro for each global variable, which expands to a reference to a local struct. The struct contains pointers to global variables. And if the struct itself is local, it will be accessed through a stack. And so at the cost of one dereference at runtime, I will have something which is safe. And this works for writing as well. So the expansion here, the one after the arrow, is in fact an L value, and I can even assign to it. So each global becomes a macro, okay? And this is pretty convenient, in fact, because the user only needs to write this into her .jitter file, and it just needs to say which variables are global, and then they can be used inside instructions with no limits. Perfect and cute. If you forget this, you can have very subtle and disastrous bugs. So it's fragile, but easy to do correctly. What you have to do for functions, it is essentially the same. For functions, I don't know, in fact, any single exception among modern architectures. Functions are also called PC relative. And so calling functions from VM instructions should be forbidden, but it is too useful to forbid. So again, I will need a mechanism to wrap them and to make them nice to use. So I can think of doing exactly the same trick, and this trick is useful. Unfortunately, so with something like this, with a declaration of which functions are used, and I don't want to switch to Emacs once more to show you, but I actually do this. If I use put C within some instruction, I can declare them as wrapped. But in the case of functions, this is not enough. Why? Because on some ABIs, calling a function clobbers some CPU resources, in particular some global register used for peak code or some floating point status register. These are actual examples I have found. These are not something I'm inventing because I'm paranoid. No, this really happens. And so around calls, in general, on some architectures, we may need to save and restore state. And of course, we want this to be invisible because it would be extremely painful to pollute user code with this low-level intrusions. How does it work? Well, we would like an expansion to a function call like this. We have a GNU expression containing a statement. This is not existing in standard C, but it exists in GNU. Then we have the pre-call code, whatever it is for the architecture. Then we keep into a temporary variable the result of the call. Then we do the post call. Then we give the result as the result of the expression. This is very painful to write by hand, but we want to obtain this as expansion. Notice that the C language is terribly defined from this point of view because void is not a normal type. I cannot declare a void variable. And so I need a special case for void functions, functions returning void. Those are important and I need to support them. And so, yes, I can support them in GNU again. And how does it work? It works using type of, using statements as expressions, using built-in choose exp and built-in types compatible in order to check if the type is void or not. It is complex but not ugly. If you git grep this into the source code, you will find the source code which is satisfying to write, and I hope it's satisfying to read as well. And in the end, it is still very easy to use because the user needs to do exactly this for functions. He just has to write wrap functions with inside the list of functions he uses, and that's it. This complexity is completely hidden. Okay. Now, another problem. What happens with RISC processors which do not have some important functionality such as division, for example, and need procedures for that? So in practice, libgcc contains some out-of-line code that is jumped to in order to implement division, square root, some maybe synchronization operation, something. Well, in some cases, it is possible to pass some machine-specific GCC option to hide this so that some instructions are not used, for example. Or, for example, struct assignment on PowerPC sometimes tries to use memcopy implicitly. I don't like that because it breaks my relocation code. So I prevent it with this trick. When it works, that's great. Otherwise, I can say that some procedures, some functions, also some C functions are automatically implicitly wrapped. Some floating point literals are also problematic, but I don't have time to speak about that. Yes, division is a problem because it doesn't exist on some CPUs, such as this file. Now, if I do exactly the same trick I showed you with the wrapping, which relies on CPP macros, some magic I don't understand, this protects with success from GCC, from libgcc functions. I don't know why it works. It should not work in my opinion, but it does. I'm happy. If by chance some GCC expert can solve this mystery, I'm interested in learning. Anyway, it seems to work. If you want to be safe, don't use division in your VM instructions, and it is always possible not to use division. You can do it differently, or you can call a function, call an external function, and when you call an external function, you're not limited, because Mohammed suggests the remainder. Yes, remainder is also an instruction that not every CPU has. Even PowerPC that has division does not have reminder, for example. But you can always use an external function if you want. Consider that division is never performance critical, so who cares if you have one function called more? Or you can mark the instruction as non-relocatable. I will show you. Some instructions, such as print, can be marked as non-relocatable here. Very simply, in the implementation of your VM instruction, you say, do not relocate this. Instead of generating a copy of this code block, generate a jump to this code block. In this way, you are much less limited. And for example, I do not need to wrap printf. Much nicer, okay? Particularly because of this. I don't need to wrap a constant string literal, which otherwise would also need to be wrapped as a global, and it is all ugly and disagreeable, and I don't want that. So if I have some non-performance critical code, so for example, division, a simple way to use whatever I want inside the instruction body is to mark the instruction as non-relocatable, and nothing will break. It costs a little at runtime, but we can probably afford it in these cases. And that's it. A solution that does not exist yet, but I plan to implement, is adding a new attribute exactly like non-relocatable. I will have dividing. The idea is that I want to make it non-relocatable only on instructions, only on architectures that don't have a division instruction. For example, on x86-64 or MIPS that I know support divisions, well, I know this will be harmless, so I will relocate it in that case and gain a little performance. That's it. So about the restrictions in the instruction bodies, what we have learned up to this point. Writing code requires care. In particular, the remark about division is important. Some divisions are harmless, some are not. Every division by a literal, which is power of 2, for example, is harmless. And that is a very common case. Division by 2 is harmless because no sane compiler will implement this with a division instruction. There is a shift instruction or a mask instruction. The same for reminder. A reminder by constant of 2 will not be implemented with a reminder instruction. It will be an AND instruction, a bitwise AND, and so on. So you have to write C, but think assembler. That is the right thing to do when you write this kind of VM code. And it's not a bad thing. It is something that, in my opinion, one should always do when writing C. If you write C, you do it for performance, so you should pay attention to it. However, you can call a C function once you wrap it, and the C function can be unrestricted C with no limitation whatsoever. And the same, if you mark your instruction with the attribute non-relocatable the same way, you can do whatever you want. Perfect. So these are minor annoyances, and it is not a serious limitation. We can have much worse problems, such as the ones I'm going to just hint at in the final part of this talk. So this, what you saw up to this point was the easy part to solve. Now we are going to freak accidents. Now, imagine that we have one specialized instruction compiled in some way. Of course, we want to replicate by copy memory from the label that I marked here at the beginning to the label that I marked at the end. Okay? The problem is that GCC might legitimately, because this is perfectly correct to do, reorder the two blocks. And the beginning could come after the end. There is no rule that says that these two labels should follow the same order as the source. So I could have the beginning at some point, which does some of the work, and then jumps back in memory. And starting from that point, I go up to the end. And so the end precedes the beginning instead of following. What happens if I try to copy memory from the beginning to the end? Well, it's a big problem because the size is negative. It's exactly not what I want. And it can even be worse than this, because it is possible that GCC, again, legitimately, might intermix and intertwine different instructions and have the one instruction begin before the previous one finishes. We want to prevent this. It would be a disaster for relocating code. The solution likely is easy, and I have a no reorder blocks option, which is mandatory. So this is a striking thing. I must compile the code with no reorder blocks. And this is why in the build system I showed you, I have to use Jitter C flags. That is not an optimization issue. This is a correctness issue. And if I want to use a JIT as generated by Jitter, I need to compile with the right options. And I will tell you what the options are. Jitter will define that variable that you can use. And if you don't do that, everything will break. So in practice, it is easy, but you have to be careful not to use Jitter C flags. Only in generated code. For the rest of your program, not using the VM, you can do whatever you want. Out of defensiveness, just at startup, the code checks that instructions have positive size, non-negative size. 0 is acceptable. The instruction can be empty, but it cannot have negative size. And they should not be intertwined. They should not intersect each other. So this is just checked out of defensiveness, just to prevent disasters. But you should not rely on that. You should compile with the correct options. A more subtle problem is tail merging. Imagine that we have two different instructions that, by chance, terminate with the same thing. They do the same things at the end. It is possible and legitimate that GCC factors the common code and compiles foo the normal way, just inserting an innocent label here, and bar, which shares the trailing part of foo, ends with a jump. So the different part is compiled differently, and the equal part is compiled in one case by jumping to the other. This is perfectly correct. See, you can do it. But if I start copying code from the beginning of bar to the end of bar, I will have disasters, real disasters here. Because it means that this code jumps out of this interval, either before the beginning or after the end. So if I'm lucky, this will crash. If I'm not lucky, it will introduce some incredibly complicated, unexpected behavior. It will jump to a different VM instruction, maybe in the middle of it, doing who knows what. So this is absolutely something we never want. So what is the solution to this? Stefan Moniz asks, can I detect non-relocatable instructions by including two copies? No, because of factoring. It is not guaranteed that the two will be compiled the same way. It is an intelligent idea, and it is a promising idea. In fact, this route has been explored by the author of the G-fault system, particularly Anton Ertl, who I admire unboundedly. I learned a lot from them. And in fact, if you look at the bibliography of these slides, you can find a paper of them. You can also find a link to my GHN 2017 presentation, which has even more links to them. So in one of the papers by the G4 people, they try to do exactly that, to help relocate their native for system. And they claim success porting from x86 to PowerPC. Then they never did anything more. The problem is that PowerPC is a very simple example, and in that case, you can detect patterns. But simply comparing two pieces of generated code for equality is not reliable. a lot of things can change due to the GOT, to the global offset table, and some instructions have very complicated way of encoding constants. For example, an example I can think of is HPPA, Precision Architecture by RISC, which has a non-consecutive encoding of bits. You can have one bit there, another bit farther away in the instruction to be part of the same constant, and so on. So no, diffing in binary like that doesn't give you, unfortunately, a reliable result. And so, I'm going back to tail merging. GCC has a -F no tail merge option, so we could rejoice. No, unfortunately, it doesn't do enough. It does not guarantee that every tail is not merged. It can still merge even if you pass this option. Unfortunately, this has existed for years and years, and it is too late to fix now. Even if we change GCC, it's a questionable idea to begin with, because GCC is correct. It is not a bug. It is just that here we would like to have a perfect control over the generated code, and well, compilers don't like to provide that. So this doesn't work, doesn't suffice for us. We need a more creative solution. The solution is, well, you will judge it. Imagine that I include some inline ASM with constraints, and I pretend to increment some, I pretend to modify in a general way some variable. I say that the variable named variables in this example, I claim to modify at the end of the code. And right after the end of the code, I modify it in a different way. And then I pretend to jump to that variable as if it were an address. Okay? Notice that the body of this assembled code is just a comment, so it does nothing. The code is harmless. But thanks to that, GCC doesn't know that multiple instructions can have the same tail. This way, I have the guarantee that I will trick the compiler into believing that no factorization is possible. This is devilish. Notice also that it is forbidden to have infinite loops inside an instruction, because if you have an infinite loop, then tail merging becomes possible. If you want an infinite loop, you have to generate a jump from an instruction to another. You cannot do it inside each instruction. So I will show you a bar instruction. It works exactly the same way, and I just generate a different text inside the comment. This is useless, but it prevents GCC, that does not understand the behavior of the assembler command, from factoring. This prevents, this does prevent some optimizations on this variable. But for reasons I don't have time to explain, the notes in brackets, Thomas, are notes for myself. Well, the variable actually used for this trick is a variable that already lives in a reserved register for other reasons. It has a special role I'm not speaking about today. And so this variable is already always in a reserved register. And the fact that GCC thinks it can change breaks nothing. I can afford it. It is even not bad for performance, so perfect. Okay, so this trick serves to prevent the kind of optimizations I don't want. So a lot of Jitter code, of Jitter internal code, is based on this principle. We can lie to the compiler. We can prevent the code from having a structure and a dynamic behavior, which is completely different from what it actually does. Notice that the code after full end, for example, is unreachable. This will never be executed. In fact, GCC generates a huge C function containing each instruction one after the other. This is how I can ensure that the register assignment is compatible across instructions. They all live inside the same huge C generated function. But that function cannot be executed as it is. That function is an organ bank from which I take pieces in order to compose my Frankenstein monster. It is only used for that. It is not executable in a correct sense. And there are many cases like that. So I have 5 minutes. I will try to not go over time. But I have no time for this. Well, okay. I can show you what can happen. I will not show you the solution, but I can show you a problem. So imagine that I have some assembly code containing a jump. Can I be sure that the label at the end of the jump will have a register assignment compatible with the position I jump from? The answer in general is no, because GCC can cheat, and instead of generating a jump to the place where I ask, GCC can generate a jump to a temporary label, to a hidden label. In this hidden label, it will do some assignments just to set up registers the right way, and from there jump where I want it. So it will introduce an indirect jump. That works, it is correct. And sometimes it can, in fact, make things a little faster. But if you do this, when I try to jump from one instruction to another, it breaks everything. And in order to make this work, I need my defect handling, which is a horribly complicated topic that I will not have time to cover today. And I need ASM Go2 in very creative ways to do that. But it can be solved, and it can be solved reliably. This is a big result. It took me at least 6 months, maybe more, really. I was going crazy with very subtle bugs until I understood that the problematic pattern was always this. In ASM code, I wanted to jump to a target, and GCC, instead of generating a jump to that, generated a jump to some different function. It performed some trivial assignment, and then it jumped to where I want. And so I was missing this. Because I patched the original destination. I have a way to counteract that. Far branches are, if you know what a far branch is, for example, if you have ever generated code for SH or for ARM 32 bits, you probably know the concept, and you know why this is a problem, and you also can imagine what the solution is. I can imagine it as well, but I did not implement it yet, so I don't have anything to show. On some architectures, it may be necessary to do a PC relative load just to materialize some constant. I mean, on some architectures, it may be necessary. It can be the only way. SH is one of those. And on those architectures, we have to raise our hands and say, we give up. There is no solution. I know no solution. Luckily, this does not happen with mainstream architectures. Okay, I will not say anything more. Now, closing. You have seen some of the devilish complexity that is involved in this, and there is more. You can see that good architectural dependent support is very difficult, and it's probably unrealistic to demand the programmer to do that when writing a VM. Only a few programmers like low-level programming of this kind, and like assembly and like portability and playing with different architectures and cross-compilers. You have seen how many cross-compilers I have and emulators. Luckily for you, I like this. So this effort should be reused, and this effort is architectural dependent, but VM independent. There is not one line of assembly in a VM specification. This is very good, because the user of Jitter is saved and shielded from the complexity. So Jitter, a generator, including this assembly code, is the right way to factor. And I need to play with fire, but you don't. And this is an important point. We should, this is a radical statement, but we should sometimes reconsider the idea of code reuse. It does not always lower complexity. Sometimes it is easier to reinvent the wheel. This is not one of these cases. I hope I convinced you about this. And Jitter VM, despite their handling stacks and registers, are in fact high level if you compare with how low level you can go. So is this complexity necessary? Well, in an ideal world, no. I would like VM generators to be simpler. In the real world, it is necessary because of its environment. I have to use C, and I have to use an existing C compiler, and I love GCC. It is the best, but still it is not ideal, and it makes some of my work difficult. The C language itself is not well defined. The CPP is terrible. CPP is unjustifiably bad. And so it is impossible to reuse C without playing with fire. And we want to keep performance because this is important. And so in an ideal world, maybe we should consider redoing things from scratch if we accept a clean cut, a clean start. And yes, I want to go on record saying that Unix is too complex. And GNU as an implementation of Unix, I love it, but is too complex, and C is too complex. And we should restart, and we should have a clean start. We should break compatibility. This is my personal opinion. If you want to learn about Jitter, okay, it is officially GNU now, so you can go to the official URL. Jitter has text info documentation, which is a manual, very, very complete. And Jitter comes with examples such as structured and Jitter list. The Jitter list is awesome. It's a complete list system. Each of those come with a manual. The structure manual is empty. It is a skeleton. Jitter list manual is a little better. However, in the case of structured, you are strongly invited to read the sources. They are designed to be easy, and I think I succeeded in that. There is a tutorial, which is of course unfinished, and you can contact me over the Epsilon mailing list, which is linked from the web page or IRC. I'm on Libera all the time, also on the Poke channel. I have this shirt. Very proud to have contributed to the Poke effort. And speaking of shirts, there will be a Jitter t-shirt at some point that I will announce on the mailing list. Thank you. That's it. Any questions? Oh, and there is a bibliography that you can look at. The copy I will publish of these slides. My pleasure. Thank you, Randolph. Thank you, Eric. Thank you, Mohammed. Thank you, Marcel. Thank you, Mohammed, for other reasons as well. He notified me about several important bugs and feature requests that I still have to handle in Jitter. So the Poke people have been invaluable, even as contributors to the Jitter effort, because many of the requirements I understood thanks to them. They actually did contribute to the effort. My pleasure. Oh, it was not perfect at all. Not your fault, Thomas. Thank you. Hello, Stefan.
I have a question. So, look, that just like in the GPOL had the same thing, is basically trying to work around the initializations by compilers. And I was wondering if there would be interest having basically changing GCs, not basically to offer a mode that's dedicated to the situation, and that would actually make the compilation faster. Because
I'm sorry, I hear you very badly. There is saturation. There are saturation peaks. Are you speaking about GCs?
No. Wait.
I think it is better now.
Is it better now?
Yes, it should be good.
So it's my system is a bit slow here. Okay, can you hear me now? Okay, so the question is would there be interest in on maybe on the GCC side to offer another interface to GCC that basically skips the optimization, so we don't have to avoid those optimizations, which would make also the compilation faster?
No, unfortunately not. GCC with no optimization generates terrible code, and which is important for debugging. So
what I'm thinking is basically having GCC be offer a way that's tailored to these kind of uses. So it's not no optimizations at all, but avoid all the optimizations that move code around, basically.
that would be lovely if I could have more control. I don't know how interested the GCC community would be. Never
Well, that's
tried
the
to
question.
attack them, if I have to be honest. Yes, of course, that would be awesome if I could avoid playing with fire. I don't think it is entirely possible because I'm not criticizing GCC here. They're doing things that are absolutely in their right. And I am playing against the rules. And so I do not expect that my requirements will be taken as a priority, but certainly can ask. I'm even surprised that the possibility exists, but now that you state it plainly, yes, maybe it is. Of course, I'm interested. Thomas says, I would need a different language than C. Well, yes, but in that case, I also want a completely different compiler. Because if I add a GCC front end to the new language, I solve nothing. All the middle end optimizations and back end optimizations are still there, and they will still break my relocation exactly as they do now. The fact that the front end is written in C instead of in Ada or in Brainfuck changes nothing. So C has some problems, but the compiler has more. And again, it is within its right. I am playing against the rules, not there, not they. So what I would like for Jitter, for reasons of personal popularity and adoption, would be to embed it into more existing software. I was thinking about GNU Smalltalk. I'm not strong with the Smalltalk language at all, and I would like to learn it, by the way, even if I'm not a fan of object orientation. But that is a small, simple VM that I think could benefit from optimization. Another more ambitious example, of course, is Emacs. And with Stefan, once we spoke in private about that idea. It's a big effort, but at some point, once the Jitter API stabilizes completely, I should attempt it. So yeah, if you have interpreters are everywhere. They're more common than one could think. And if you have a simple interpreter or a bad JIT, this is a good way to replace it. I think I will shut up. Thank you, everybody.
Thank you.
Luca, I don't understand the remarks that you just made about, because Thomas' suggestion, I don't know if he's been serious, but basically, I mean, if you will write the, I mean, if the Jitter users will write the instruction bodies in a language, in a domain-specific language, for which you write a front end to GCC, And sure, I mean, offering the possibility of calling C functions from it, then you could actually, in your front end, you could have, what?
I think that you are right in a sense, but that is not a GCC front end. That is a completely different unrelated compiler. And that is possible.
Excuse me? What did you, sorry, I did not get that.
Different unrelated compiler. It is no longer a GCC front end because I have to have my own optimizer. I have to prevent the GCC passes from running. Most of them or all of them. And then, of course, I can jump to C functions for compatibility, and that is fine. But my code needs to be handled by my own middle end and back end. I cannot reuse GCC. It's a different compiler. And yes, maybe it will be simpler, but I will not benefit from the GCC optimizations, which do help, by the way. I am benefiting from GCC here. It is not that GCC is only getting in the way. No, some of the good code quality I get is thanks to GCC. And it is not only by a political preference that I use GCC. If you try to do this with Clang, it will fail horribly. You just don't have enough support. No, it will not work. This can only work with GCC. If you use Clang or TCC, you are restricted to the slow compatibility model. You have no JIT. And
okay, I think we are miscommunicating, but okay, we can move this to offline.
You think that I should write a GCC front end?
No, I mean, I think that Thomas was suggesting that maybe you could use some sort of built-in, annotations. So you could annotate the tree and then to make GCC do what you want internally or be better for you, right? So, like, for example, he mentions this unique attribute, which is internal to GCC. You cannot mark in C a function as unique, but if it is supported internally and you will add, a built-in in the C language for it, then you could use it. Now, if you will use your own language and your own front end, then you will not need to actually add additional built-ins to GCC in order to annotate your tree and to maybe, be more creative.
Listen, thinking about going back to the last slide about the ideal world versus the existing world. In an ideal world, I would do exactly that. I will write everything in epsilon and I will make epsilon reasonable.
Yeah, but you don't need to write everything. I mean, you say that you are.
It would be a smaller task than playing with fire.
Yeah, but I mean, you don't need to build everything. You just said yourself that you are basically the jitter file, so the VM, right? All the instructions are basically blocks which are built into a function that you qualified as your bag of organs, which, by the way, I think it's a very nice metaphor. And and you said also that if you call a function from a jitter instruction, then the function, there are no restrictions, right? It's just that big function that you are compiling. So you don't need to basically restart everything from scratch. It is just the instruction bodies. And okay, I know that in POC, we are not very good in that because we have very big and complex instructions. We will change at some point. But ideally speaking, the instructions, they must be simple, right?
Well, in POC, you have instructions that are currently too big for my taste. But
yeah.
Not violating any rule, you can do it.
Okay, I understand, but it's not everything. You don't have to reinvent everything. Or I mean, if you would use this hypothetical new language, you would only use it in the jitter file, right?
No, I would use it for everything. It would be my language, of course.
Okay, so, but then then we are miscommunicating. I mean, this will be a language in which your users would write the instruction bodies.
No. Look at the slides. Unix is too complex. C is too complex. I don't want a plethora of embedded languages which are each too weak. I don't want another M4, another Oak, another Perl, another C. Should have
Really?
one good language. Yes.
But you are implementing a tool precisely to implement languages.
Because this needs to.
Okay, no comment. Okay.
Even in the ideal world, and forgetting the one language idea, I think that the language of instruction bodies should be Turing complete. Do you agree?
Oh, yeah, absolutely. Yes.
You see?
Yes.
So we don't want it to be weak, or at least I don't want it to be weak. I think that you believe in embeddability a little less than I do. You dislike the idea of having a domain-specific language on top of a list, for example. I do like the idea. You don't, if I remember.
Yeah, well.
Philosophy difference, but
anyway, this is a tangent anyway, so yeah, we can discuss this offline.
Sure. Well, thank you for your interest.
No, thanks to you for the nice talk.
My pleasure.
Okay, so if there are no more questions, then we have like 15 minutes break now, and then Mohammed will do the talk about the Trojan poke. Okay, so thank you, Luca, again, and see you later, everybody, in 15 minutes. Thanks.
Later.
Now it's recording. Thanks.